Log on, tune in, find out. Another good idea from Cambridge.
I'm very pleased to be here. I am a Bayesian statistician, as will become apparent. I spent 4 weeks here at the beginning of the program, and it was very interesting talking to many climate scientists. Our conversations were about practical details, but a lot of them were also about the high-level questions, about the big framework in order to understand things. So I thought that would be a helpful thing to do today, would be to lightly touch on the big picture of how all the uncertainties fit together. So everything I do will just be pointing to things, and please, if anything you think, oh, actually that's exactly what I need to do, then please we'll pick that up. Just find me afterwards. Okay. Thanks to many collaborators that I've worked with. I've been very lucky to do that. Okay, so let's go. Okay, so the subject of my statistical expertise is mathematical models implemented as computer simulators. Okay. There's a nice quote here from the person managing the Oxford Supercomputing Centre. Whenever possible, everything's done in the supercomputer. Look at Formula 1, same in the aerospace industry. You do all the modelling in the supercomputer and then do just one real-world test, which is handy for climate because we are just going to do one real-world test. Okay, so it's clearly we're glad of that. Okay, so obviously working with computers and moving them to the real world raises many questions. And so my first statement is that there is a general methodology that's not directly climate science related, but is much wider for how you move from understanding from looking at computer simulators to going to things in the real world. There's a particular website that I'm part of, the Managing Uncertainty in Complex Models initiative. If you just remember the 4 letters MUCCM and Google them, you can go to that website. There'll be references, papers, there'll be a toolkit, and it will give you some sort of slightly larger picture of the things that I'm talking about. Phew, now that I've plugged them, I can now not feel guilty about not plugging them anymore. Okay, fine. So all of these problems, climate problems, rainfall runoff models, modelling the whole universe, modelling a Formula 1 car, they all look very different, but they all have an underlying structure. I was very happy that Matt set a lot of this structure up yesterday. You have a simulator, very, very complicated, but it's a function. Okay? So we have the function takes whatever inputs we choose to give it, and so they're the system properties, and it turns the system properties into system behavior. Okay? And it does it in differently, obviously, for different areas. In the climate model, well, we all know all the things we've been talking about. We take various physical parameters and we add to them things like CO2 scenarios, and we look at things like what will the global climate be in our one-time experiment on climate. Okay? So there are a lot of things we want to do. Obviously, we get a lot of qualitative insights every time we have a model, but also we want to learn about the parameter choices, and I'll tend to put a star by something if I mean the, in some sense, right value of it. We want to know how informative the function is for predicting what will happen next if we run the function at the appropriate value. What will that actually tell us about the future? Okay. We want to know how much use historical observations that we may make are in constraining, validating, etc. the model. If we have decision inputs, we would like to choose them wisely. Okay? And so in the climate model, well, we have historical observations, there are things about climate we want to predict, and the decisions will be various policy relevant things we might want to think about. Okay? So let's take this through in stages from the easiest version to the real version and see what happens. So the simplest version, okay, observations are made without error. The function is a precise representation of the system. Okay? So Z is what we see. Z is a function historically of some true value of x which we don't know. Okay? Then in principle, it's easy to say what we have to do. We have a function, we just invert it. There may be a unique inversion, there may be a family. Having done that, we can then just take the function which we've inverted, which is exact, we can project it into the future, Okay? And we'll either get a single projection or many. If we have decision choices, we can then just optimize. It's easy to say. Let's remember, while we're doing this, that inverting and optimizing complicated high-dimensional functions is a challenging technical problem. Very clever people spend their entire lives doing this. There are very many sort of learned journals on doing this. Okay, so even the simplest version of the problem is actually very hard. So let's hold that thought. Of course, the first thing we say is that, well, anything we're using to constrain the model we observe with error. Okay, so what we observe is not the historical values, but the historical values with errors added on. So I'm going to write that. So I'm going to use this thing plus with a little O around it to imply that I have two things that I'm adding together, and they're either independent or they're uncorrelated or whatever, depending on the formulation. Okay? But so the problem is exactly the same, but I don't find out what my historical values are. I find out some error things on top of that. So I can do this. Okay? So what we now do is what we call statistical inversion. Okay? It's more complicated because I have to effectively invert not just for one value, but kind of a range of values and then reweight. And so there are challenging numerical and statistical problems. Again, there are people who devote their entire lives to statistical inversion. Okay? And again, there are journals that will tell you the latest techniques for much simpler problems than the climate models that we're dealing with. Multiple solutions, whether there are any, is potentially a very big issue. Okay? Now, everything I said so far ignores possibly one of the largest sources of uncertainty, because most computer models in climate, but in everything, there's a whole bunch of other quantities that are not explicitly written in your X. The things we might call the condition uncertainty. So there are initial conditions, there's boundary value conditions, there's forcing function conditions. Most models, when you actually see an experiment run and you're trying to invert it, there's a whole bunch of parameters that they held fixed because it was just too complicated to vary them. Okay? So hidden behind your apparent experiment is a real experiment. Okay? And you can spend a lot of time working with a computer model before you realize what the real experiment was. Okay? So our function with the X that we vary has a whole bunch of things which we hold fixed. And the things we hold fixed are usually vastly more complicated than the things that we vary. That's why we don't vary them. It's like the entirety of a specification of all the things that force climate. Okay? And so effectively the idea that we would have liked to have done is to have evaluated your function at, in some sense, the best choices. So now, obviously every slide that I give could be a whole talk if I was smart enough to give the whole talk. Okay? So in particular, condition uncertainty is a very deep and important subject which has many different ways of being dealt with. So the simplest one is just to suppose, and I've been in many, many experiments like this, that the condition is actually just been set. You know, so I find out eventually, well, with the forcing function running on that, oh, but we had some values, we just put them in. Okay? So there's a run. Okay, there are other versions that I do where, in fact, the function you actually are given is like 10 different forcing functions, which they then average. But so this is just something that we can do, so I can do it on a slide quickly. Okay, so there is additional uncertainty introduced by the fact that we have condition uncertainty, and effectively, well, there are many, many ways of doing it. Here are two simple ways. In order to do it, you need an experiment. You need to vary the condition. Okay? And if you're fortunate, you can do many variations of the condition. If you're less fortunate, you can do some, but some is better than none. And effectively, there are two ways of thinking about this. Well, there are at least two ways. The simplest way is simply to see roughly how much your output changes as you change your conditions. Okay? And so you might write down a representation like this. Okay? You just put an order of magnitude. You say, well, effectively, this output changes by about 10% when I change the conditions. That output changes by about 5%. When one of them goes up, the other one tends to go up. So you create a simple probabilistic representation, which again is obviously an approximation. It's better than not doing it. Okay? What would be better than that is to recognize that, well, firstly, you would like to make this an explicit function of your condition, but your condition is just too big to put in there. Okay? Any individual parts of it that you wanted to pull out, you might then move into the parameter space, but we've done that already. Okay? This is all the massive stuff that's left. The other thing we might recognize is that as we change the condition, it will have more impact for some choices of the parameter than for others. Okay? So we might do a rather richer modeling where we say that the function that we would like to evaluate, f of x c star, okay, which we can't because we don't know c star, is the thing that we can evaluate plus an uncertainty representation which depends on x. This is clearly a very large subject as how we would create such a representation. And all I'm going to say at this point is yes, there is theory. Okay, so I put down rather cryptically there are natural exchangeability representations to help us to do this. And if anybody would actually like to try representing their condition uncertainty properly, I can. I mean, there's a lot of work that's been done effectively on exactly that problem. Okay, so that these things are, in principle, I can tell you how to do them. In practice, well, who knows? But in principle, I can. Okay, yeah. Everything I say, in principle, I can tell you how to do. In practice, it's always interesting. Okay? So now everything here appeared like we just run the function a whole bunch of times. As we know, we can't do that. Luckily, Jonty's talked about emulation. Peter's going to talk about emulation. So we understand that emulation is going to come in, and we're going to emulate like loads of stuff. Okay. So effectively, if the function is expensive to evaluate, you have to recognize that you have to treat the function as an additional source of uncertainty. You only know the function at the places where you've evaluated it. Okay? So you need an uncertainty specification for the function as well, because you're uncertain about it. Okay? And that's what an emulator is. It's simply what I know about the function in the places I haven't evaluated, given where I have. So it can be thought of as an approximation to the function and a measure of how good the approximation is. Okay? So again, emulation is a subject. There's masses of stuff on the Muckham website about this, and emulation, emulation is probably the best studied part of moving computer simulators to the real world. Many people have interesting views on this. Kind of the simplest thing is to have a global sort of like simple statistical bit plus a bit that's left over. Okay, so here's a bit of an emulator. It says I'm going to create some polynomials perhaps in some of the inputs, and then I'm going to have a bit left over because it's obviously not a perfect match. So I'd have it would look just like a regression, but what's left over actually has is a stationary stochastic process. So mostly the things, I expect the things that Peter fits will look kind of like that. Okay, and so there are interesting questions here about how do you run your experiment effectively to choose this, and design of computer experiments is a subject. In fact, I think there might even be a book written on the design of computer experiments. Okay, we have different statisticians will have their favorite tricks, and they will do it in different ways. And expert judgment and diagnostic analysis all are a key part of that. Now, the point that I would like to emphasize out of this is that you now think, okay, well, had CM3, can I really do that? Had GEM, am I going to be able to do that? Okay, so what happens if you have if you have a kind of slow emulate sort of function, you can run it kind of a lot of times, and you can kind of emulate it. If it's really slow to evaluate, then the whole notion is you create linked emulators. Okay. So, as Jonty said, he once had CM3 effectively as an entry drug to emulating HadGem, okay? And he may even want to go further, okay? That he may say, okay, we have an emulator for HadCM3 that may actually direct, or inform how we actually emulate a HadGem, okay? So this is a notion that if you're trying to emulate an expensive function, probably there are other functions around which are informative. Because what I said was that an emulator reduces is about your uncertainty about the function, and you have other pieces of information about that function rather than the function itself. So the simplest one would be if you have a fast version, you cheat on all sorts of things, you cheat on the time steps, you do all sorts of stuff. When you build a complicated function, I think it's good practice to build the fast approximation to it while you're doing it, if you actually can think ahead as to what uncertainty analysis you want to do. And then you can make many runs of the fast. You then fit your emulator to the fast, okay, and you then make fewer runs of the full, and you treat the fast one as a prior for the full, which you can then update. Okay? So there I show you just very quickly some sort of thing I could do. I could write down my fast as a regression that I can fit because it's fast, and then I can update by running on the full sum of our values. I can click my fast one onto the full. And the heuristic about all of this is that you need loads and loads of runs to get the qualitative form of your model right. You need far fewer runs when you have the qualitative form of the right to get the quantitative form right. If I have many variables and I'm trying to fit a regression model, loads of runs you need to get the form of the regression model. If I knew the form or had a good idea about it, far fewer runs to pin it down, which is one of the reasons that I always stress that in practical emulation, you need a good regression term in there. It has two reasons. I mean, it has many, many functions, but one of the principal functions is to allow you to snap from your fast to your full model. Okay. So now, we can now say what I call an internal uncertainty analysis. You've specified a prior beliefs about what the inputs are, a likelihood for your error, a probabilistic emulator for F, and in some way or another you've treated conditional uncertainty. Along comes the data. You then update using Bayes' theorem. And the point about Bayesian methods is that you can just say they just happen, in the sense that we have a joint probability distribution for everything. Observing, we make our observations of something, and then we just condition through. That's Bayesian statistics. Okay. So that's a natural Bayesian treatment. Okay, I call that an internal uncertainty analysis because once I set up my model, it's all the things that I can do by operating on the model and all the things that I can't avoid doing because they're intrinsic to the way I set the problem up. Okay, so it's conceptually straightforward. Technically it's difficult, particularly constructing emulators is hard, dealing with condition uncertainty is hard, and there's a lot of computational challenges in doing the Bayes analysis because it's all multimodal and the likelihoods are bad, but the principle is straightforward. So let me just talk a little bit about what you might do when you've done this. Okay, so you might want to calibrate, which is exactly this thing about figuring out what values of x star you like. Are there solutions? Are there no solutions? And etc. Forecasting, that part's clear. Control, or at least influencing the system. These are the things we might want. And let me just make a comment on this slide, is that I said that I'm a Bayesian, and as a Bayesian I know that there are two ways of doing this. You can do a full Bayesian analysis where you specify all your beliefs about everything, a full probability specification, and then you do a full probability analysis. Everybody in the world would understand that as a full Bayesian, as a Bayesian analysis. I personally don't prefer not to do that. I prefer doing something called a Bayes linear analysis, in which I specify far fewer quantities, just means, variances and covariances of the quantities, and I might make transforms of the quantities, I might take indicator functions of the quantities, but at the end I create a much simpler structure, and I do what's called a Bayes linear analysis, which is based on a simple prior specification and effectively linear fitting. Okay? And just as there is a full theory of full Bayes analysis, there is a theory of Bayes linear analysis. And the reasons for my preferences are, well, the full Bayes analysis is great if you can do it, if you can make a meaningful prior specification, and if you can do the analysis, in which case, if you can, brilliant, you should do that. If you think, oh, this is very, very hard, there is an actually easier thing that you can do. The Bayes linear analysis is faster, it gives you partial information, but it is much faster, it's more robust because it doesn't require so much of many things for you to put in. Okay? And in particular, there's a very fast forecasting methodology that is embedded in this. So later on, I'm going to just make a comment that if I want to do a decision analysis, I have to look at many, many different sort of versions of this. How can I push them all forward into the future? the fast forecasting methodology in the Bayes linear world makes many things possible that would be very hard in a full Bayes analysis. Okay? So I'm just leaving that there as a point that if you think, how can I really do the full Bayes analysis, you do actually have an alternative. Well, you only have an alternative, I think, if you're in Durham. I don't think anybody anywhere else does it. But if you're in Durham, you get a note from your mum that says that you don't have to do a full Bayes specification. And you can just get on with it and just solve the problem. Okay? Let me make another comment here about, I talked about calibration. That's you make your observations and then you learn about the true value of x. Okay, so I want to point out in your mind that maybe you don't want to do that. Maybe you want to do history matching. So why would we have concerns about learning about the true x star? Firstly, as I said, there's a lot of non-robustness in the calculation, in the Bayesian calculations. So you might not be actually happy about the technicalities. Secondly, you might not particularly feel there is a unique true value for your model. Why should you? And then you might be not even sure whether there is a unique true value, but you might not think that there could be any true values. Okay? So a simple alternative, and I think this has probably come up several times before in people's talks implicitly, in fact probably it was kind of linked to what Matt said, I think, was that you can do what's called history matching. So you go around each possible choice of inputs, you don't ask is it true, you ask do you think that were you to run the model at that choice, you would get sufficiently close to what you've actually seen that you can't rule that out as a plausible sort of value to be used in going forward into the future. Okay? So if you could actually run the function at every single point, you could just do this everywhere. Of course you can't, but your emulator can. Okay? So effectively history matching goes all over the parameter space and just decides which x's to keep, which x's to throw away, and putting all the uncertainties that we've described in. Okay? And the thing is, funnily enough, that's actually quite a fast and straightforward thing to do. Okay? Particularly in the Bayes linear world, so we can, this is a very practical methodology. Okay? So Matt said that he kind of tried this and he didn't get much restriction of the parameter space, but I think that's probably because he just got bored. Okay? Effectively, you do it, you emulate, you restrict the parameter space, you resample in the parameter space, you re-emulate, okay, you re-restrict, and our experience is that each wave that you do sort of constricts further and further because you have higher density, the functions become simpler, they become easier to emulate. So that this is actually a good practical methodology. Okay? I also point out that the things that we've been talking about model discrepancy, when I talk about matching to reality, I can say, I can go around the various sort of things I'm trying to match and say, I should match that one pretty well, that one not so well, that one much less well. It's very easy to build model discrepancy into this description. And even if you're going to calibrate or data assimilate or any of these other things, it's a good idea to do a history match first, just to reduce the space to the physically sensible space. And so I do think in your mind, having history matching in your tools is a useful thing. Fine. So we've now gone through the internal analysis in principle. Okay. So now that's a lot of work. Okay, but it's all very clear in principle. Okay. So is that the right thing to do? Am I telling you that you should do this? Okay. So what about the limitations? If the model was a precise representation of the system, then what I told you would have been exactly the right thing to do. So the only unknowns are the true values at which to and the function, etc. Okay, then everything would be cool. Okay, but we know that's not the case. Let's step back and think a minute why that's not the case. So a physical model tells you how system properties influence system behavior, and with all sorts of complexities. But that's what it does. There are two kinds of simplifications. Firstly, the properties are approximated because they're too complicated and we don't even know them. Okay? And secondly, the rules for turning system properties into system behavior are approximated because of mathematical details, simplifications for tractability, because we don't know the physical laws. So we have two layers of simplification. Neither of these, I mean, that invalidates the modeling process. In fact, that's why models are useful. But it only becomes problematic when we pretend that an uncertainty analysis of a model is the same as an uncertainty analysis of the system. Okay? So the thing is that models don't generate statements about reality. Okay? This is why I called the first an internal assessment. As an uncertainty analysis of the model. Okay? We now have the external uncertainty analysis, which is an analysis of the system. So now this is where I want to get to. So Matt showed you a simple way of doing this. He said, well, you could say that the model isn't exactly right, so we'll put in an extra lump of uncertainty to get you from the model run at its appropriate value to the system. Okay, so that we often do that. I mean, a lot of people do. Okay, that is called like the structural discrepancy. You put some specification into that. Large variance of a component means that you really think the model's a bad representation. Okay, condition uncertainty that I talked about before often gets absorbed into that. You know, that because we're not running at the right condition, we have a thing. So when I added a bit of uncertainty to my model before for my condition uncertainty, you could stick that in there. I mean, I prefer to keep them separate, but you can do that. Okay, and then the key part here is the covariance structure. So if my model tends to underpredict here, will it tend to underpredict in the future, or will that bias kind of go away? Okay. So let's talk about the value of doing this. Firstly, even though that sounds a little bit crude, it's always better to recognize uncertainty than to ignore it. Even if your modeling is partial, it's better than to say there is no uncertainty. Even using such a simple form for discrepancy is a big advance or step over not doing it. So just stick in some uncertainty. Just say plus or minus 10%. What the heck? You know, it's better than saying there is that directly matching your model to the real world. Okay. So if you actually do this, then you can. I think it would be hard to find anyone who would call you on that and say, you know, because relatively that would be. I mean, now we are coming to what is pretty much the state of the art, mostly. Okay. So what I said before about the internal uncertainty analysis is that it didn't distinguish between the simulator and the system. So have we now fixed up the problem by putting in the external uncertainty analysis? Okay. So I now want to get to the my key point of the talk about the meaning of our thing. The meaning of a model analysis, if it's purely internal, okay, is a model analysis. Okay. The external analysis is meant to be an analysis of the system. What we do when we actually put together those two statements, that we have observations which are system plus error, system which is the sort of the model plus error, we will end up with a collection of uncertainty statements about system properties and system behavior. Okay? So the question is, what do these uncertainty statements mean? We're now going to get onto meaning. Because we can casually talk about the probability that we're headed for climate disaster, whatever, and casually and in the pub, that's fine. But for science, we want to be, I think, a bit more precise, I hope. Okay? So here's a quote, okay, from a typical quote from the BBC website. Fortunately, rapid climate change is an area that the UK has taken the lead, blah, 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 blah. So the rapid climate change program, the aim of which is to determine the probability of rapid climate change occurring. The probability of. Okay? So my question is, what does that actually mean? I don't mean what does rapid climate change mean. I mean, that's a problem itself. What does rapid mean? What does climate mean? But what is assuming we could work that out, what is the probability of rapid climate change occurring? And this isn't just like the way that the BBC talks. Here's I am a member of the Rapid program, okay, and where Danny is our PDRA doing this, okay, and this had the following premise for the call. Okay, so what are the implications of rapid watch, and in particular, the risk is taken to mean the probability of rapid change in the MOC. Okay, the probability, and there's a whole bunch of things, but they make it quite clear that we're not talking about models here. We want to make sound statistical inferences about the real climate system. So I'm in this project. I'm signed up. What did I sign up to do? You know. The thing is, I'm fairly sure that nobody who wrote this actually could answer these questions. And I do know this because there was a sandpit, and I talked to the people there, and they didn't know what they meant by that. So I am on safe grounds, I think. I mean, they were very. I mean, it's a great project, but there are fundamental questions. You know, not just in this project, but in all attempts to go from models and uncertainty to actually the world. Okay, so now let me reveal my colours. I'm a subjective Bayesian statistician, and one of the reasons I am is because I can understand it. In fact, the main reason. Okay, so in a subjective Bayes view, any probability statement is straightforward to say what it means. It's the uncertainty judgment of a specified individual expressed on a probability scale. Okay? So we don't say there is the probability, there's my probability. Just like the uncertainty doesn't have an absolute meaning. If I think, so if I don't know how much money you have in your pocket, okay? So I'm uncertain about it, okay? But that's not the uncertainty. You may or may not know. You would have a different uncertainty. It would be hard to imagine a project, even though no one would fund it. But suppose we had a project to assess. Supposing we had a project that we are going to assess the uncertainty about the amount of money in your pocket. That would be a daft statement. There is a lot of uncertainty, but there isn't the uncertainty. Okay, so we have uncertainty, but we don't have the uncertainty. Okay, and this is the point about the subjectivist Bayes view: is that it puts it back uncertainty where it's supposed to be. Uncertainty is a statement about what an individual knows. Okay, so this has an agreed and testable meaning. So therefore, I can see how we can actually do this. Okay? Now that doesn't settle the question about what any of these things mean, but it allows us to talk about it. So let's come back to that thing, the probability of rapid climate change occurring. And we said, what does that mean? Is it a property of the world? Does climate have a probability of rapid changing? Okay. Well, in the subjectivist view, the probability statement is a judgment of an individual, so not the probability of rapid climate change, but Anne's probability, or Bob's probability, or your probability, or your probability, okay? These things are all meaningful, and we can understand them. Okay, now there's an issue of perception here, though, because most people expect something more authoritative. I mean, if that's the BBC website had said, the aim of the RAPID project is to figure out Dave's probability of rapid climate change, you say, well, why Dave? Yeah, or Matt's probability. I mean, you say, well, yeah. But so that is a serious issue. But in fact, the issue I think is more serious. It's not that, even though people want it to be more authoritative, the sad fact is that it's not even that authoritative. Because any time I see a stated probability, okay, if at least you could attach one person to it, you would be happy. But in fact, stated probabilities usually are not the judgments of anybody. I don't know whether the UK SIP probabilities were anybody's. I've never found anyone who signed up and say, yes, that's exactly what I believe. Okay, so we don't have the meaning that we would like to attribute, people will be disappointed by, but they should be more disappointed because it doesn't even mean that. Okay, so I think it's not unreasonable that our analysis should be probabilities which at least one person signs up to, and more obviously would be good. We can ask, is that a sufficient objective? Now, I can just say a pointing thing. Okay, I'm very conscious as a subjective Bayesian, so I'm a subjective Bayesian. Okay, people say, well, supposing you're not. Okay, well, surely there are loads and loads of other meanings of probability. So, can we use some of those? Okay, and all I want to say here is that there are many, many versions of probability, but most of them, when you actually unwrap them, are modelling constructs. So they live beautifully within an internal uncertainty analysis. Because in a model, it makes perfectly good sense. You can put a P in, it's the probability. You can have a relative frequency, it's in the model. Everything is fine. The hard part in every other interpretation I know is you can't take it out of the model and make it and attach it to the world. So if you can, that's brilliant. Please tell me. As far as I know, the only way I can understand for extracting uncertainty from the models and placing it in the world is this way. Okay? So that's why I'm a subjective Bayesian. So, as I said, I used to worry about whether model uncertainties actually did correspond to expert uncertainties, but then I realized that's just the wrong question. I mean, an expert could say, oh, yeah, you say we're just a lazy expert, if Homer Simpson runs his model, he says, yeah, that's what I believe, and he eats his donuts and stuff. That doesn't make it a good analysis just because he believed it, okay? So the big question is, why do we think that the probability of an individual is scientifically valuable? And so we now get to the heart. Okay, so the individual has to be sufficiently knowledgeable for their judgments to be worth listening to, and the analysis has to have been sufficiently careful and thorough to support this judgment, and sufficiently transparent that the reasoning can be understood and engaged with by other people. Transparency is really important here. You can't drop that out. You can't somehow say, oh, well, somebody did something, we elicited it off somebody and he's gone now, but that was his view. And so we want be knowledgeable and to be transparent. Okay? So I think that it's fair to say that the objectives of a serious analysis should be to produce the best current judgments in a sufficiently transparent form that their reasoning is open to critical scrutiny. So I always talk about not is it someone's opinions, but is it their best current judgments. Okay? So effectively, best expert judgments, what does it mean by best? I would say that best effectively means that the expert has done a really careful job and there isn't anything else that he or she could feasibly do that would change them a lot. Okay? So I think that's a reasonable criterion. If the problem's important, we're going to tell that every government in the world and every person in the world to completely change the way that they live, okay, then I think that best current judgments is a meaningful and rigorous standard for the analysis. I'm very correct. Yep. So if an expert is giving out their not best current judgments, they should say, this is my second best current judgment, it's my fourth best current judgment, it's not my very good judgment because I was just too busy and I wasn't funded to do this, but seeing as you've asked me for a number, here it is. Okay, yeah? We should stand up and actually attach ourselves to these things or distance ourselves. Okay? So if we actually do this, okay, so if we actually follow this, okay, then this approach, we would see that science goes this way. Firstly, an individual expert forms a best current judgment. That's a pure subjective analysis. The next stage is that all of the uncertainty judgments of a whole range of different experts are then put into the picture. And then we have a scientific analysis because we have effectively captured the views of the community. Not why just Dave, well, everybody who has an interesting opinion to contribute. And eventually we hope that the analysis could become so clear and compelling that everybody would agree. At that point we could talk about the probability of rapid climate change because it would be an agreed sort of shared social construct. Okay? So how are we doing so far? Well, I don't think we're doing very well at all. Okay, I'm not sure that anyone's making a careful specification of best current judgments. Okay, I've never seen anyone stand up and say, this is my best current judgment. Maybe I missed you. So partly because scientists just don't think that way. Scientists like living in their models. Statisticians aren't that much help, frankly. Policymakers don't know how to, they don't know they're not getting the best current judgments and they don't know how to ask for them or why they should. There's no funding mechanisms for formulating things like that. Best kind, who cares? Okay, and it's hard. And it's hard because it's different, because we're not used to doing it. Okay, but for policy development, this is the basic question. Okay, we are required to give our best current judgments. If you went to the doctor, you want his best current judgment about what you should do, not his summary about what that data set says, what this theory said, whatever. You want the doctor's best current judgment as to how you should be treated. So does the planet. Okay, so as I said, best is a high standard, but I don't see why we would aim for less than that. Okay, and the point is that it's difficult, but it is not more difficult than all the things that we do about collecting the climate data, building and analysing climate models themselves. It's just a different difficult thing. Okay, so oh crap, I want to get to the heart of the core talk now. Is that the big issue that we get wrong, which is the whole thing about linking models to reality. Let's see if I can do this really fast. Okay, so how do we link models to reality? Okay, so that why are models telling us anything about reality? What is the analysis that we have to do? Okay, so evaluations of a simulator are informative for a physical system. Okay, because as I said, models tell you about how system properties affect system behaviour. Okay? And so if every time you run a model, you're getting some insight into how system properties influence system behaviour. Okay? If I have a whole bunch of models, they're all informative because they're all jointly helping me to understand how system properties influence system behaviour. Okay? So if I want to think really seriously, in a grown-uppy sort of way, about how my model links to reality, so firstly I have to think about the relation between system properties and system behaviour, which of course I don't know. It's now another unknown, but my model is going to help me do that. So it's an unknown quantity, so I can emulate it. Sometimes I call that the reified model, just because the word reify means to treat an abstract concept like a model, as if it was a real concept, the actual relationships. Okay. Having done that, we can imagine that we take our model and how do we link it to reality? First, we think that our simulator is an approximation to the reified form. And secondly, we think that the reified form even itself Okay, if you put in the appropriate values, still may not have captured everything about the system properties that we're talking about, so there would still be a difference on top of that. Okay, so here's our verifying principle. A simulator is informative for the real world because it's informative for the verified relationships. The verified relationships are informative for the world. So this is a picture that everything that I talked about up to now was you have a model that links model evaluations to f of x. You stick the best input in, put in a discrepancy, put in an error. Okay, but in fact I say no, you should do it like that. Okay, we interpose another function. Okay, and if we have several simulators, they all point into that function here. They're all jointly informative for f star. You don't think each one of them, it might be the winner. Each one of them is telling you about that f star. Okay, so how would we do that? Well, in one slide, well, recognizing uncertainty is better than ignoring it. So the simplest way of doing it is to say, well, here was my emulator, okay, for f of f. So my emulator for f star might be, oh, well, I'm going to put some uncertainty about what the b coefficients are in there. I'm going to add a new u star thing in instead of u, and then I'm going to add a new, to add a bit of extra stuff. Okay, I could build that really quite quickly. I could do it in 10 minutes, or I could do it in a year, depending how carefully I do it. Okay, and then doing it in a year would be what I call structured verification. Okay, so I could do that with sort of like with more care and more structure. And if I'm going to do calibration and forecasting, then if I'm doing the Bayes linear approach, everything here has been about the modeling and the science. All of the methodology that follows on from that will just be exactly the same as what I told you before. Everything is just changing the joint covariance structure. Oh, right. So now I'm ready to draw a picture for you. Okay, so it was said yesterday maybe we should be involved in the problem of determining how much it's worth investing in changing the behavior of the world. So let's try and draw a picture that actually has some of this stuff on and a decision on. So the red stuff is stuff that you see. So you do a series of evaluations of the model at different conditions, from which you do that clever exchangeability representation. You pull out the stuff that you need and you stick that into whatever you need to create the reified form. Okay, and then you build the reified emulator. The reified emulator gives you beliefs about what would happen if you ran the reified function, okay, at true. You link that to the historical observations with error. You link that to the data that we see with further error. Okay. Supposing we had a multi-model ensemble that we were talking about, that comes off there, and we analyze that kind of in clever Bayesian ways. Let me not talk about that. Okay. Now we do our fast approximations. Sit down here. Of course, I'm doing this in the wrong order. You'd actually do your fast approximations to determine what stuff you need to take out at the top, but they're in there. You then put in. Supposing we want to make our decision, let's suppose that that's too complicated to add decision variables to, but you can add decision variables to your fast version. Okay. Then you can then link across the stuff. P is the stuff we want to predict. That goes into there. We then add that to create our emulator for the future, stuff we want to predict as a function of our decisions. And there we go. So we've now got the true function there. Our decisions as to what we could remediate go into there, and there's a cost function at the bottom there. Okay, so this is the diagram that we would want to solve. Let me make a handful of comments about this. Firstly, this is an influence diagram. So this is a conditional independence graph. I draw these arrows not just for to be informative, but to be strict. So conditional independence graph, things children are independent of ancestors given parents. You can do local computation calculations on these. They're very powerful tools. Secondly, see all the different kinds of uncertainty on there. Okay, I mean, everything on here is all sorts of different uncertainties, but the subjectivist view kind of holds them all together. Thirdly, as I said, if we have more models, they'd all join at the F star stage, so we can click them in. Fourthly, notice that X star doesn't go into the function. We're not trying to fit the function on X star to Y. We're trying to use a function to create our views as to the relationship, and that's what we calibrate to reality. So we don't calibrate our function at all. That's just, if I think carefully about it, the wrong thing to do. the decision here I've rather simplified. Really, the decision is based on a whole series of steps. We make our policy now. We observe in the future. We observe climate. We will observe more modifications of our functions, and we'll get more and more information about the F star. We can further modify, and that all lives on that diagram. And, for example, Danny has written a very interesting thesis about exactly that part of the decision structuring. Okay, so this is a picture that you should imagine this is a part of a larger picture. Okay, but it's sort of it's the kind of thing that I'm talking about. So now this is my concluding slide. So to assess best current judgments, it's enormously helpful to have an overall framework. We can think about, everybody thinks about their bit of it, but somebody needs to be thinking about the big picture. There are challenges, but they're no harder than all the other modelling, computational and observational challenges involved with studying climate. Either we solve those decisions on that diagram, or we then pass them over to David Cameron. We say, sorry Dave, we can't do it. Could you do it in your head please, and just do something. And of course, there was a comment yesterday about we should do all that's humanly possible. It is humanly possible to do this. It's not what we're doing, but we could do it. Okay? But there's a lot of work involved. I mean, it is a similarly difficult process to all the other things in climate science. So what we actually need, I think, is a large-scale planned program of cooperation joining up many interested individuals. And we could call this, I don't know, I can't do acronyms, the Climate Uncertainty Project. We call it the Big Climate, so Big Cup, I don't know. But we need people to work together at a high level in order to do this. Okay? Obviously, it would be great if this was recognized and funded, but this is the real world. So let's just say, as is clearly the case, that judgments about actual climate are desperately urgent. So we can't wait for some wise old guys to say, yes, that's exactly what we want to do. So we should start the project. Unlike the massive supercomputer stuff, really it's our time is the key. It's not a computing issue, I think. It's an understanding and thinking issue. So this could start informally. People could just do it. And it has to really be, I mean, everything here is, I mean, statisticians can help, but this is a job for climate scientists. Everything on that picture was science, and the statisticians help structuring, so I can help structure all of that diagram, but the science is for climate scientists to do. And if we did that, then we would have best current judgments that were best. They would be meaningful. We could know exactly what they mean. They'd reflect our range of agreement, disagreement. They'd influence policy because policy would be there, and everything would then would make sense. So I just leave you with a few references. They happen to be all mine just because So that first one is fast forecasting methodology. The next one is all about Bayes linear things. That's verification. That's the stuff about designing and linking models at different levels of stuff. The galaxy formation one is a big study on history matching. So in that one, we history match the whole universe. Okay, and the condition uncertainty is the state of all the dark matter in the universe at every moment of time and space. So clearly we can't measure that, but we require it to run the model, but so we do it. And so there's a big discussion on history matching in there. And stuff about external and internal, there's a recent thing that I wrote. Fine, thank you very much.
Well, thank you very much. On the clock, we've only got a minute left, but I think there's some really challenging, you've thrown down some challenging gauntlets there, so I'm sure some people must have a few comments on those. Yep.
Yeah, a recent example of this, what is it, intrinsic uncertainty versus external, on the development of the Boeing 787 Dreamliner. They used an incredible amount of computer analysis on the aerodynamics and modeling the flight control system, setting parameters. And about a month ago on a test flight, the flight control computer caught fire. And the whole program's delayed about 6 months. The reason was external debris in the system. But if you look at climate skeptic websites and some of the public debate, a lot of the objection to climate modeling is that somehow the potential for foreign debris simply invalidates the entire process. How can you make a convincing argument against that?
Well, I can't make a convincing. The question is whether that's a good argument or a bad argument, which is a science question. I mean, it may, but all I can say is, firstly, okay, is that we can have informed views about it, and we can say why our views are informed, why we think what we think. If we think that that's the key weak point in the model, not just our model, but in the modelling across the world, okay? I mean, this is why I say about this being a shared structure, then people then have to actually work out what their direct analyses are, or what their surrogate analyses are, and then in the end, I mean, there may be legitimate disagreement about this. I mean, I say, I don't know. So I can't, or there may not be. It may be when you do analysis, it's completely clear. If you say, okay, of course it's completely clear, then obviously there's an analysis you can do that would show it was completely clear. It's a trouble with climate skeptics. I think there were two positions that they take. Firstly, they think that, I mean, if I told you that there was I don't know, a 1 in 3 chance that an axe maniac would come round and chop you up into little pieces, you might say, aha, well, I'm sceptical because there's a 2/3 chance it won't. Okay, and so you have to make it a probability 1 before I'm going to do anything. Okay, so there's extreme skepticism, and there's the other thing that says, well, I'm not sure that you've actually done the proper calculations to even get that 1/3 number. And I have quite a lot of sympathy with the notion that you haven't, that the climate community could do more to actually to get their genuinely meaningful uncertainty numbers, and then we could embed them into policy. Okay, but sorry, I probably haven't answered your exact question because it's a science question and I'm a statistician. But in principle, I think that we could just talk about it and we can look at how we model it, what information is relevant, and either the expert community agrees or they disagree for reasons that they have to make transparent. Hi.
Yeah. So, final question from Tim.
It's more of a comment than a question. I mean, I liked your last slide about this sort of dialogue about uncertainty, but I feel one thing we need to engage more with, say, your statistical community and my, let's say, climate community, is coupling the statistical analysis with physical understanding. So, for example, you might have a climate model which represents momentum coupling to the surface by a diffusion scheme with parameters. And so you've got a statistical framework which says, okay, I don't really know what the values of those parameters are, and let's emulate statistically the behavior of the model. But in truth, it may be that the actual momentum transfer from the atmosphere to the ground is due to waves, which are totally not representable at all by diffusion. So you're kind of wasting your time actually looking at details of parameter perturbation.
Yeah, no. This is why I made my big emphasis here. Okay, this is a science picture. It's not a statistical picture. Okay, and what you're telling me is about what happens at that level here, not at what the model here is. Okay, and you sorry. Oh, yeah. Okay, yeah. So this is okay. So in this science picture, the model is up there. Okay, yeah. But what you're telling me about is all sorts of interesting information about the quantities in which I really want to put the parameters in. And of course, it's a bit unfortunate in my notation that I use the same x's here and here, but somehow I knew I was going to have like half a minute at this point. But really, these are, I mean, there's an extra level of modelling between the things that really actually affect the relationships between system properties and system behaviour, and the things that we put in our models, which are obviously the cuttings on this.
Estimate perhaps
yeah,
that.
yeah, but so the point is that precisely at the science level, okay, that's why we actually distinguish what the actual relationships are from the things that we put into our models. And many different models may contribute different aspects of that, which is why I also said that they all fit into that thing. This isn't the model we actually run. It is our conceptual thing that is what is part of the thing that joins together all the things, all our data, all of our general heuristic ideas about the theory, all the models that we can build. And it's that, so it's a conceptual, but it's a science map.
Okay, I mean, I think that is a discussion that will probably continue informally, maybe over a few beers, and probably some progress could be made over a few beers, I think there. I think we should draw that session to a close there, so thank Michael again. That was on the overhead projector. Sorry, two. That was on the overhead projector when I came in this morning. So read it.